an ionic equation, we are taking anything that is AQ and we are splitting apart into its positive and its negative ions. The solids do not split up at all. They stay together. The reason why they're solid is because they're more attracted to their own atoms than they are to the water molecules. Then you cross out anything that's the same on the left and on the right-hand side. Once you do that, what you have left over is called the net ionic equation. This is important because it takes the overall chemical reaction and it tells us what is actually reacting in that chemical reaction. In a sense, the NO3 negative is like a taxi. It's attached to the silver nitrate so that you have a solid crystal. Once you dissolve it in water, that nitrate isn't involved in anything. Writing out a net ionic equation is important for the next step. In the next step, you have a table where you list the reactants, which are Cu, Ag positive, on the bottom, you have the products, Cu2 positive, and Ag. What is the charge on that copper atom?
Nothing.
Nothing. It's neutral. Good. You can tell that there is no charge because there is nothing written up here in the top right-hand corner. As soon as you see something in the top right-hand corner, that becomes its charge. So this tells us that there is a 1 positive charge. In the products, we have Cu2 positive in our net ionic equation. That means this has a 2 positive charge. There is nothing up here. It is neutral, so there is no charge. Our question then becomes, well, if copper starts off as neutral, how come it becomes 2 positive?
Because it's being put together with another element.
Sydney?
The copper photons are more attracted to the NO3 negative electrons, so the copper lets go of its electrons to the Ag so that it can be combined with the NO3 negative.
Exactly. The process that you just described is electron transfer. So let's go back to our Bohr models. If I have copper, copper is number 29, which means it has 29 protons. It has 29 electrons. How many of those electrons go into the first energy level?
2.
2. A little bit of hesitation there. Second?
8.
8. So now we're up to 10. Next?
16.
8.
Oh, damn it.
Then the next one,
16?
we can go up to 18. Do we need all 18?
No.
No, we only need
8.
11 electrons.
I just guessed.
In that last energy level. So the copper atom has 29 positive charges, 29 negative charges, which means overall
0.
no charge. If I tell you that copper has a 2 positive charge,
It has 27 electrons. Wrong symbol.
how many electrons does that have?
27.
27 electrons.
Sorry, not simple.
The only way it can go from being or from having 29 electrons to 27 electrons, is if that lost 2 electrons to something else. The copper began as a neutral atom, but it became a 2 positive charge because it lost 2 electrons. Why does the copper seem to disappear?
Because it's in the solution.
Why does the copper seem to disappear? Think back to the demonstration. You started off with a copper wire in the shape of a tree, but after a while the copper wire got thinner and thinner. We can see the copper wire because it's composed of many thousands of copper atoms. Once these copper atoms start transferring electrons and making this becomes dissolved in the solution, and we cannot see it anymore because they exist as single copper ions. That is simply too small for our eyes to see. We say that copper was oxidized. O-X-I-D-I-Z-E-D. Because it has lost electrons. If I were to write this out as a reaction, and I had copper ions to begin with, and I was left with a copper 2 positive charge, when I show a loss of electrons, I show it on the product side or the right-hand side of the equation. Think about it. We know from balancing that the left side has to equal the right side. Copper is going to have 29 protons and 29 electrons. On the right-hand side, this copper has 29 protons and 27 electrons. By having an additional 2 electrons, now my subatomic particles are the same on the left and on the right-hand side of the equation.
So all you're doing there is just trying to balance it?
Yes, in a way you are. This is called an oxidation equation. Oxidation is always a loss. So what I want you to do is take a few moments and work on the silver side. Silver starts off as a 1 positive ion. It becomes a neutral substance. Tell me why. Tell me why you think it appears out of nowhere and suddenly I have a silver Christmas tree. We know from our overall net ionic equation that silver starts off as an ion that has a 1 positive charge. We form solid silver, which is actually the silver colored crystals that you saw collecting on the side of the copper wire. Solid silver is an atom. It has 47 protons and it has 47 electrons. The silver ion still has the same number of protons, but it does not have the same number of electrons. If it has a 1 positive charge, what is the number of electrons that silver has?
46.
46.
You said 46.
What's happening here? Yes.
The solid silver has an equal amount of protons to electrons.
How is it that it's all of a sudden having the same number of electrons and protons?
Gained an electron.
It is. If I add 1 electron to the ions in the silver solution, that means that substance is going to have 47 electrons.
How does it gain 1?
In order for something to gain an electron, something has to lose an electron. The reason why silver ions are able to gain electrons is because copper has already parted with 2 of its electrons. Those electrons simply flow in the watery environment, and when they connect with the silver ions in the solution, that silver ion will gain an electron, and then silver atoms start collecting together, and that's why I see the crystallization. As an ion, I can't see this because it's a singular substance running around in the water. It's only when it's in atom form and it starts grouping with other atoms that it is a solid. According to the balance of this equation, way back here, how many parts silver do I have?
2.
You have 2 silver ions here and 2 parts silver atoms here. Another way to think of this is, if you lose 2 electrons, something else has to gain the same number of electrons that have been lost. This equation only shows that silver is gaining 1 electron. So overall, in order to fit with the balancing idea, you actually need 2 parts silver ions for every copper that gives up electrons. Yes?
So copper gave off 2 electrons, but silver only needed 1. So two copper electrons are equal to 1 silver electron.
You've got that switched. 1 copper will need 2 silver to pick up the electrons it loses.
So silver will need 2 electrons to pick up 1. I'm just
No, you're still mixing them up. Each copper loses 2.
yes.
Each silver gains 1.
There's 2 silver.
So I need 2 parts silver to gain 1 electron from copper, and then the other one gains the other electron from copper.
So you get double the silver.
Okay. Would it make it easier if I perhaps showed it like this?
And that's why you want to do.
So here what I'm trying to show is that copper loses 2 different electrons. Each electron is picked up by 1 silver ion to make 1 part silver atom. The second electron that it loses must also be picked up by something. That will be another silver ion that is in the solution.
So on the left side, does the electron that the silver loses cancel out the electron that it gains?
Yes.
So then
That would be a net reaction. That's why you do not see electrons appearing in that equation, because the number of electrons gained and the number of electrons lost cancel out.
So if copper only lost 1, would any part silver be able to pick that up?
Yes. Yes. It could. If for some reason something was influencing the loss of electrons, absolutely.
What part would more likely be picking up? The liquid state or the solid state of silver?
Aqueous.
Aqueous.
You would need an aqueous state in order for ions to be free enough to pick up the electrons.